roots tell you everything that you want to know. So if you know the simple roots, from that we have already seen in some detail how to get all the positive roots from there. And since the negative roots are just their adjoins, you know all the roots. So you can get all the roots out of this. Then you can, the next part that we just mentioned, but we did not really do in detail, that's what I'm going to do today. That's the algebra. How do you get the algebra of the Lie group, starting from the simple roots? And the final part is how to get other representations. When I say other representations, I'm stressing on the word other simply because the adjoint representation is the one we have been working on in so far. And the adjoint representation, of course, the action of the generators or action of the representatives of the generators on the vector space essentially is via the commutation. So if you know the algebra, that exactly is the adjoint representation. So once you have found out the algebra, you know everything about the adjoint representation. But what about the other representations? And is the other irreducible representations? Can I find them out just from the simple roots? The answer is actually we can. At least for a semi-simple Lie algebra, we can find out almost everything from the simple roots themselves. And that last part, I'm not sure I will be able to do today, simply because I've not looked at it again, so I'm not sure how to sort of explain that in the easiest way today. But that's because primarily I'm stuck with a calculation for this part. So I will want you to follow along and help me out with it. So let me just remind you how this went. The basic idea was, given any pair, of course you know this, that is, given any alpha, you have a minus alpha. And E alpha, E minus alpha, and alpha dot H, these three form a closed algebra. In particular, if you choose the proper scalings, which is you divide E alpha and E minus alpha by the length of the vector alpha, the root vector, and divide alpha dot H by alpha vector square. These are just relabelings, of course. These are just rescalings of these operators. These give you E plus, E minus, and E3. This is something we have already done several times, which essentially gives you an SU2 Lie algebra embedded in whatever Lie algebra you're talking about. And you basically use this SU2 Lie algebra to learn about various properties of the algebra. So the only thing that you have to remember really is that the commutators of these E plus, E minuses, this one is E3, E3, E plus minus. As for the raising lowering operators of SU2, is plus minus, E plus minus. The only tricky thing is, well, not really very tricky, but there used to be a factor of 2 in the SU2 Lie algebra that you had studied in your quantum mechanics. There's no 2 here, which essentially means these E plus and E minuses are 1 by root 2 times the J plus J minuses that you had used before. So there will be an extra 1 by root 2 wherever E plus E minus acts. That's the only thing you have to remember. And the other important point is that because we have to deal with many different SU2s, one for each alpha minus alpha pair, we will sometimes write something like, say, E plus with alpha in a bracket here, which will just indicate that we are talking about raising lowering. With the raising lowering, or, well, E3 for the alpha minus alpha, alpha dot H subalgebra. Okay. Usually when it's clear with which one we are talking about, we will not write this. Okay. The alpha label we may very well omit if we are clear from the context or from whatever we have said before, which raising or lowering we are talking about. Okay. And just to remind you, this was the important quantity that we had to deal with, which essentially is the E3 value, nothing other than that. And E3 value essentially tells you how many times you can raise minus how many times you can lower. Right? That's standard in any SU2. The current M value will tell you how far away you are from the reaching the top. Well, actually it can't, right? Because the M value alone can only tell you, J and M together can tell you that. What M value can tell you is this difference between J and minus J. That is, how many times do you have to raise to get to J? How many times you have to lower to get to minus J? The difference between that, that's in M itself. So that is what we used to recreate the root structure and so on. So what we will do today is first we will try to recreate the algebra using this. So let's do that. Let's do the simple one for which I have no confusion at least first. SU3, we did talk about this, but let me just remind you what we did there. SU3, of course, had two roots, and not two roots, two simple roots, alpha and beta, which were half root 3 by 2 and half minus root 3 by 2. Of course, this had the properties that alpha square and beta square, the lengths were both 1, and alpha dot beta happened to be minus half. Simple, they were at an angle of 120 degrees with each other. So, which is why SU3 had this Dinkin diagram. Remember 90, 120, 135, 150, these were the angles. So the number of lines just show you which order you are at. 90 is no lines, 120 is just one line. So now this alpha dot beta equal to minus half, or this result tells you that this actually is a result which tells you if you start with E beta and try to raise or lower it using alpha, what happens? And this, of course, is minus 1, and minus 1 tells you that since this has to be P minus Q, and Q we know is 0, because you cannot lower beta, right? E beta minus E alpha. If beta and alpha are roots, beta minus alpha cannot be. So, cannot be a simple root, sorry. That was what I wanted to say. If beta and alpha are simple roots, then beta minus alpha cannot be. So Q has to be 0. So P is 1. It means you can raise E beta once. That's essentially what we already know. That is, we had alpha beta to begin with. These are the simple roots. And this is at the phi 1 level, at the phi 2 level. We know you can get alpha plus beta. Of course, this makes it obvious that if you can also start with E alpha and raise it using the raising operator for beta to get to the same alpha plus beta, and obviously you can, and no surprises there, you end up with, by beta mod square, which is the relevant quantity to calculate for that. For SU3 is very, very simple. You again get minus 1, which says P is 1 for that as well. And what that is telling you is 2 alpha plus beta, alpha plus 2 beta, these cannot be roots. So this is what all that we have done before. Okay, we have done it for SU3, we have also done it for G2. So basically this essentially tells you that once you have hit alpha, beta, and alpha plus beta, you are done with all the positive roots. You cannot have any more positive roots. And then you also have the negative roots, 3 more, and 2 kata generators. So the algebra has to be made out of 8, and that's it. 8 generators, and this has to, so and the structure of the algebra, at least what are the basic generators, we already know. Now comes the question about the commutation relations. How do we get to know them? For that, all you have to remember is the adjoint representation works this way. Right? In general, not only for E alpha, E beta, add A acting on B is A commutative with B, number 1. And we know that their adjoint representation is a representation. That means it obeys the SU2 algebra, or obeys the original Lie algebra for whatever Lie algebra you're talking about, in this case for SU3. And so if you look at the adjoints corresponding to E plus E minus and E3, you will get an SU2 subalgebra back. So now the real question is, if you talk about E plus minus alpha and E3 alpha, that is the SU2 subalgebra generated by E alpha, E minus alpha, and alpha dot H, and ask what it does to E beta. When you say what it does to E beta, you mean what the representatives of these, which are the adjoint operators, do to E beta. Then the answer is sort of pretty straightforward. You know this is SU2. These three together form an SU2 Z algebra. You know that E beta can give rise to one more state, right? From here, you can go to E beta plus alpha. And you also know that you cannot go any further beyond that. So what does this tell you? This tells you that these two states together must form an invariant subspace. And from our knowledge about SU2 algebra, we already know that if you have a two-dimensional invariant subspace, which is invariant under the action of SU2 algebra, what does that subspace correspond to? That must correspond to a spin half representation, right? The good thing is for SU2, we know everything. We know what its representations are, we know what their dimensionalities are, and so on. So we can easily identify that here, for this SU2 Lie algebra, okay, this E beta essentially is the same as this state, half, that is the J, M, I will put that in, and I'm just putting in an extra label of alpha simply to remind you that this is the SU2, this is the representative, this is a state which forms part of a representation of the SU2 Lie algebra generated by alpha. So what will the M value be here? Okay, that's a question. Answer this.
Minus half.
Why?
When E plus acts on E beta, you get another one. So this has to be the lower one.
Okay, that's part of the story, but the real answer would be when E minus acts on this, you get 0. That's why it's the lower one. Right? That's the real answer. Your answer is correct because with only two possibilities, that's the only thing that's left. But the real issue is E beta is the one which has to be killed by E minus alpha, so has to be the lowest weight state of this SU2 algebra. Has to be half minus half. Okay. So if you ask what happens when E plus alpha acts on E beta, that is, of course, it's the adjoint representations, axon means commutator. What will you get? That's the E plus operator acting on the lowest weight state in a spin half representation. What's the result? I know it has to be E beta plus alpha, of course. But more than that, we know something more. We know the factor in front. Or, first of all, we know it has to be half alpha, right? If you are using the SU2 way of writing this thing down. But in front of that, there should be a factor. How much should that factor be? Come on, SU2 spin half is the easiest in the world. The factors are also easy. You should sort of memorize them.
1 by root 2.
Okay, anybody with a difference of opinion? None. Yeah, it is 1 by root 2. Well, it would have been 1 in the standard SU2 that you had learned. That's why I said it's the easiest in the world, right? In the SU2 that we studied in quantum mechanics, S plus acting on the downstate gives you the upstate, S minus acting on the upstate gives you the downstate with no factors in front. No factors simply because there you were using the standard Sx plus minus Isy. Here you are using an extra 1 by root 2 simply because your E plus E minus are defined with an extra 1 by root 2. So this is what you are going to get. Actually, there's a bit of a catch here. The point is you know this has got to be 1 by root 2 half of alpha. And you know the half of alpha has to be essentially E beta plus alpha. But like in all quantum mechanics scenarios, you could have had a phase factor here. Instead of 1, there could have been extra eta. Simply, simply because you need to identify which one of, say, when E alpha plus commutator with E beta gives gives an operator, you know it has to be proportional to E beta plus alpha. And you know that proportionality factor has to have a magnitude of 1 by root 2. But is it 1 by root 2 or e to the I alpha by root 2? Well, you don't really know. That's where you have to make a choice. So what you do is you choose this eta to be 1 and hence define E beta plus alpha to be the generator which corresponds to the commutator of these two objects, times root 2, of course. So that's really a choice of phase which tells you that E alpha plus beta is root 2. I've dropped the plus and bracket alpha simply because for this algebra is simple. E plus alpha is E alpha, right? Because just to remind you, E plus is 1 by length of alpha times E alpha. Here, for this particular Lie algebra, the length of the vector is 1. So you get this. Okay? Is this part clear to everybody?
Yes, sir. There should be no vector sign on top of E, right?
Oh yeah, there should be no vector sign on top of E, of course. You're right. E is not a vector. Alpha, these roots are vectors. Very often we will not even put vector signs on top of the roots because I'm assuming you know that we are talking about roots of vectors. But anyway, let's try to be consistent as long as we remember to. But okay, you're right. There is no vector sign here. Okay, so what have we got here so far? Not much. We have seen that we have three positive roots, E alpha, E beta. And we have found that E alpha plus beta, the other positive root, is actually the commutator of E alpha, E beta, which, by the way, we already knew. And we knew that from the basic theory. What we have got is that the factor is root 2. So we have got exactly what the commutator of E alpha, E beta is. Okay. But what about the other commutators? There are of course 8 generators here for SU3, out of which for the Karta, we already know. There are 2 Karta generators, we know their commutation among themselves is 0. They don't commute, they commute among themselves. We know that when you take the commutator with E alpha, commutator with E beta, commutator with E alpha plus beta, you are going to get alpha times E alpha, beta times E beta. That is alpha I times E alpha, beta I times E beta, alpha plus beta I times E alpha plus beta. That is, those are known. Commutators with the Karta generators are known from the very definition. So what else do we need to know? We need to know the commutators of E alpha, E beta, E alpha plus beta with E minus alpha, E minus beta, E minus alpha plus beta as well. Right? That will complete the whole algebra. Is it okay with everybody? I don't mean you just need to know in fact, you know E alpha with E minus alpha, by the way, already.
Sir, could you repeat this again?
So all I'm saying is, okay, let me just remind you that these are the 8 roots. There are 8 generators. There are 2 Karta generators, 3 positive roots, and 3 negative roots. When you say we want to describe the entire Lie algebra for SU3, it's not enough just to tell me what the generators are. You need to tell me what the commutation relations between the generators are, right? That's what the algebra means here. Now, commutation relations of HI with any of the E's, whatever that E is, I'm deliberately writing W, so, or I should write R maybe, not for root, because it works for all 6 of them. It's simply RI ER, right? That's how you define what the ERs are. So this much is done. You know this. You know E alpha's commutator with E alpha is 0. You know E beta is 0, etc. So those are trivial. You have already found out E alpha beta E beta's commutator. That's 1 by root 2 times E alpha plus beta. But you need commutators between everything. So what you need more than that? You need E minus alpha's commutator with E alpha, which you know, by the way. You know E alpha, E minus alpha, right? And also E beta, E minus beta, also this, because this is simply alpha dot H, right? That commutator is known. We have already figured that out from the theory. This was done from the definition itself. This follows from the sum of the theory that we have done, and this works not only for alpha minus alpha, it works for beta minus beta, alpha plus beta minus alpha plus beta as well. So those commutators we know. What we need to do is find out this E minus alpha E beta, E minus beta E alpha, and we all also know how much these are, right? How much are these?
Zero.
Beta minus alpha, so 0, yeah.
Yeah, 0. Because there you cannot lower beta. That's so you know this, you know E alpha, E beta minus beta E alpha. Again, these are all known already before you get to this stage, right? This was a definition. This is a result we had already proven earlier, and these are known from the theory that we have done. So what else do we need to work out? We need to work out things like whatever we have done so far has not told me what this is going to be, right? Or this.
Won't there be like the first commutator might like E, can't it be E beta and the second one as E alpha?
Yeah, there will be, but the fact is, when I say algebra, I need the whole thing. I know this will be proportional to E beta, has to be. This one will be proportional to E alpha. Again, that's from theory. When I say algebra, I also mean the whole thing. That is, what are the factors in front? So how do I figure them out? That's the question. Of course, I could have continued along the list a bit. I could have said, what is the commutator of E minus alpha plus beta with E alpha and so on. But that's sort of trivial. You can just take the adjoint of this relation and you can get that.
Jacobi identity.
Okay, there are two issues here. That's exactly one of the things you would use the Jacobi identity. Or, well, you could use the Jacobi identity or you could use this property, which is essential Jacobi identity. This, as you can easily see, is the Jacobi identity, right? I just move two of the terms to the other side. Except that the way I've written this should remind you of something else, which is some other operation has a property very similar to this. That is, you're doing something, which of course is add A.
Superoperator's commutation.
No, not really. What we are doing is this. This, of course, is a Jacobi identity. I'm not denying that. I'm saying that if you can also look at it upon it as a slightly different thing, or in a slightly different light, which actually reveals something about a structure. What is this? You had some kind of product, right? Remember the Lie algebra, this commutator is the Lie product in that algebra. Okay? And when you're applying this operation on the product, what is the result? The result is the operation acts on the first term of the product. Second term stays intact, right? Remember the product, the commutator is the product. So you're essentially doing this. Just to remind you, this is what you did in elementary class 12 math, right? a product on which the differentiation operator was operating. And what did you do? You applied d on u, then multiplied it by v, then added to it u plus u with d acting on v. You realize that this is exactly the same thing. Lie product of b and c, on that when you apply add a, you essentially have add a b and c's Lie product plus b and add a c's Lie product added together, which is exactly this property. The same property that the derivative has. Okay? So this is called the derivative property for this particular operation. In fact, it actually shows you that commutation is like a derivative, which, by the way, should not come as a surprise. That's what quantum mechanics is based upon, right? The basic fundamental equations in quantum mechanics essentially tells you that derivatives end up becoming commutators, equal to commutators, right? Not derivatives don't become commutators. I'm saying all those equations for any function's derivative is essentially a commutator of that thing with h, if it's a time derivative you're talking about. The derivative property simply tells you that you can essentially also treat commutation as if it's like a derivative in terms of products. You already knew this for, by the way, this is not new. You already knew this for this, right? Ordinary product. You knew that this will work. Hopefully everybody remembers this, and you have used this often enough. This is, of course, telling you that the commutator has the derivative property. It's just another fancy way of looking at it. The same result. It's nothing new. This is just something which follows from the definition of the derivative of the commutator. This follows from the Jacobi identity immediately. But it just, keeping this in mind, sometimes makes life a lot easier. Instead of using Jacobi identity every time, but everything is on one side, then you have to write the thing on one side and move it to the other side and so on. Just remembering that the commutator works like a derivative makes it easy to calculate various results. So as Monica said, we could use the Jacobi identity to find out this thing. Why the Jacobi identity is coming into picture? Because we already know that E alpha plus beta is E alpha E beta's commutator times root 2. So we could use a Jacobi identity here to rewrite this in terms of commutators we already know. Or you could use a derivative property, which is E minus alpha gets to act on E alpha. E beta stays intact, and then of course you have to take the bracket of the whole thing. That's one term. The other term would be E alpha stays as it is, E minus alpha, E beta commutator is what you have. This is the second term in the derivative property. Again, whether you want to call it the derivative property or whether you just say that this is just the Jacobi identity written on the other side, makes no difference really. It's just that remembering that it's like a derivative makes it often easier and faster to work out what's going on. Okay, now, next step. Among these brackets, on the right-hand side, you have commutators. Actually, you know all of them. What's the first one? Let's go in steps, the inner commutators. How much is this?
Alpha dot h.
Not really. Careful. Yeah. It's not alpha dot h. It's close.
Minus alpha dot h.
It's minus alpha dot h.
Yeah.
Right? E alpha, E minus alpha is alpha dot h. This is the negative of that. What about this commutator? How much is this?
That one is 0 because
That one is 0, right? Notice that we are using the results we already know. This one is 0, this one is minus alpha dot h. And now you know what this is. This is going to be minus alpha dot beta e beta, right? And this is half. Minus alpha dot beta is half, so you get 1 by root 2 e beta. So we have found out this commutator. Although, let me just tell you, as George also points out in his book, this one you did not need to really use the Jacobi identity or the derivative property or whatever you call it. Why? Because we already said E alpha plus beta essentially is the half alpha state, right? For the SU2 Lie algebra with E alpha, E minus alpha, etc., this is the half state. And E minus alpha is a lowering operator. So if you hit this with a lowering operator, where will you go? You will go to half. Which, by the way, is E beta. Right? So this result actually would have followed from the fact that we already know the representation of the SU2 Lie algebra. You hit it with E plus, it goes up with a factor of 1 by root 2. Hit it with E minus, it comes down with a factor of 1 by root 2 again. Why 1 by root 2 in both cases? Because basically that's exactly what the spin half algebra tells you. Is it okay? Yes?
Yes, sir.
Okay. So this one I did not really need the Jacobi identity for. I could have got this from the fact that I'm just lowering a state which I've raised once. So you have to go back where you were, and the factor that you will get is simply a result of the algebra. But this one, of course, will be E alpha times factor. But what factor? Now, here you might say, why this has to be 1 by root 2 E alpha for the same argument, right? Why? Because E alpha plus beta is what you get when you raise E alpha using the E beta operator. And now you're loading it back again using E minus beta. So it would seem like the same argument that we had given a while ago would tell you that this has to be 1 by root 2 E alpha. Just SU2 again. Once again, E alpha, remember, is the lowest weight state, something which cannot be lowered any further for the beta subalgebra. And since there are only two states in that subalgebra again, that also is a spin half thing. So this factor seems to be obvious. But it also is wrong. Can anybody tell me why? What's wrong with this argument that I've given right now? Yeah? Am I still there? Do you realize why? Have you understood my argument? Why it should be 1 by root 2 E alpha first?
You are trying to draw a connection with the way you did E minus alpha, E alpha plus beta.
Yeah, I'm using the same argument. So how can that be wrong? I'm telling you the answer is wrong. Okay, how do you check the answer is wrong? Simple. Just use the Jacobi identity in this case. What is this going to be? Root 2? Well, I'm going to just drop the first term because I know it's going to be 0. E minus beta E alpha. Just going to write this as E alpha Then you have a E minus beta E beta commutator, which is minus beta dot H. Right? So how much is this going to be?
Plus alpha dot beta.
Yeah, it's going to be plus alpha dot beta E alpha. But since alpha dot beta is minus half, this is going to be minus 1 by root 2 E alpha. So notice that this does not, of course, match our prediction here. The question is, what is wrong with the argument I just gave you? The correct answer is this one. Correct answer is this. After all, the Jacobi identity is a basic part of Lie algebra theory. So if that tells you something, it has to be correct. So what was wrong with this argument of mine?
Because we defined E alpha plus beta as commutator of E alpha and E beta, and not E beta and E alpha.
You're almost correct. Yeah, not only almost, you're actually correct. It's just the wording. I would have chosen the wording differently. The point is, what I did was I took the SU2 Lie algebra generated by alpha, applied the raising operator of that algebra to E beta, found a state, that is, found a generator, which I knew has to be proportional to E alpha plus beta. And there I had a choice. I knew that the factor in front would have to have a magnitude of 1 by root 2. But that the factor has to be 1 by root 2 is a choice. There I chose, but when I chose that, I already made a phase choice. Right? Once I've made the phase choice, E alpha plus beta is given. So this argument that when I hit E beta by E alpha, I'm going to get E alpha plus beta again, or E alpha plus beta by root 2 again, of course cannot be correct. In this case, you know that what you will get, as Monica was pointing out. You have to get minus 1 by root 2 E alpha plus beta, right? You have to get, okay, sorry, I'm running out of space on the margin here. I'm no Fermat, but anyway, the margin is too small for me to write whatever I wanted to write. The page is too small. But anyway, E alpha, E beta, I already have defined this as 1 by root 2 E alpha plus beta. That leaves me no choice but to say when I hit E alpha by the raising operator for the beta's Lie algebra, I must get minus 1 by root 2 times E alpha plus beta. Once you have made a phase choice, you have to live with it. You cannot repeat that, change that when you come around to the other algebra. You're talking the same operator, remember. So that's crucially important. Phase choices once made has to be stuck with, which is why this argument will not work. Is this clear to everybody?
Yes.
Okay. So now we will quickly come to the one which has been giving me some trouble. That is, I find it difficult to match what Georgia has said. A small matter of factor. But you know, factors can get very nagging, and I kept on trying to do the calculation and kept on missing a very simple factor. Might be my problem. Of course, it's very possible that I've made a stupid mistake somewhere which I can't catch. Okay, let me just write down the generators for you. We'd already worked out G2. Okay. So G2, of course, had this two generators, alpha, two simple, sorry, not two generators, two simple roots. G2 was this one. This is a Dinkin diagram for G2, an angle of 135 degrees. And these are the simple roots. So some housekeeping stuff. That's straightforward. Alpha dot beta obviously is minus 3 by 2. So twice alpha dot beta by alpha mod square, which remember is a p minus q for the E alpha subalgebra, works out to be minus 3. Minus 3 by 2 divided into 2 divided by 1. Whereas twice beta dot alpha by beta mod square is minus 1. So this tells me for this Lie subalgebra, P is 3, Q of course is 0 for both of them. You can't lower either beta in the direction of alpha or alpha in the direction of beta. And here P is 1. So this already told us quite a lot about the Lie algebra. He told us that alpha, beta of course are positive roots. They told me the 2 alpha plus beta, sorry, not 2 alpha plus beta, let's start with alpha plus beta. Then 2 alpha plus beta and 3 alpha plus beta are positive roots, right? And then after a bit of work, this is what you get at the very outset, but you also manage to see that 3 alpha plus 2 beta is also a positive root. I hope you remember that. That you went to 3 alpha plus beta and asked, can I raise it in the direction of beta? So which means you took the beta dot 3 alpha plus beta dot product multiplied by 2, etc., and found out whether it can be raised. It turns out that it can be. So you get 3 alpha plus 2 beta. So 1, 2, 3, 4, 5, 6 positive roots, 6 negative roots, and 2 katta. So 14 generators in all. They're much more involved Lie algebra than the SU3 one. Okay, so the question is, how do you find out the commutator? So the easiest ones, the ones we already know, let me just not worry about them again, right? E alpha is 0 and so on. You know H1, H2 is commutator with all of these 7 and the other 7. You also know E alpha, E minus alpha is alpha dot H. All that stuff we know. We also know E beta, E alpha, E minus alpha, E beta is 0. You can't lower. But now, let's start. Let's talk about this. So let's label. We're using E plus alpha. You must get E alpha plus beta up to a factor. What I'm saying is that you can find out what the factor is. So what will the factor be? Can anybody tell me that? Yeah. This is an SU2 representation, so you figure out what the factor will be. Question is, which SU2 representation do we have here? E beta is a state in the SU2 representation of add, essentially the representation of add E plus, add E minus, add E3. Because E plus, E minus, E3 are E plus alpha, E minus alpha, and E3 alpha. Which representation are we talking about?
So there are 4 roots: beta, alpha plus beta, 2 alpha plus beta, and 3 alpha plus beta that is accessible from E beta.
Right. So this is essentially a four-dimensional space that we are looking for.
Yes.
Right. So which representation is this?
I don't.
3 by 2.
Right. This is a 3 by 2 representation, and E beta, in fact, has to be the lowest phase state because it can't be lowered any further. Right? Which is why, Monica, I objected to your argument last time. You said you could raise this, that's why it is minus 3 by 2. Which of course works fine for spin half, but spin 3 by 2, you can raise minus 3 by 2, you can raise minus half, you can raise plus half. The one you cannot raise is plus half, plus 3 by 2. Okay? So here, just the fact that you can raise it does not tell you that is minus 3 by 2, but the fact that you cannot lower it, that tells you is the lowest wave state. So of course, what you said was perfectly correct for spin half, but for spin 3 by 2, this argument still works. You can't lower this, right? So minus 3 by 2 has to be the case, and I'm just putting in the alpha label here. So when you hit this with E plus alpha, you of course will get a state which is proportional to 3 by 2 minus half alpha, which is of course E alpha plus beta times something. So what is this times something? What is the factor in front?
Root over 3 by 2.
Root over 3 by 2. How do you figure that out?
I mean the usual formula for the root over t to t plus 1. But okay, I'm not
Yeah,
sure
it's
if that.
actually, no. Yeah, your answer is right. It's actually root over j minus m into j plus m plus 1
Yeah. And
by
so,
root 2.
yeah.
And here j is 3 by 2, m is minus 3 by 2, j minus m is 3. J plus m plus 1 is just 1. So you get root 3 in the numerator and root 2 extra from the fact that e plus alpha has this extra 1 by root 2, the definition. And once again, there is a matter of choice of phase here. I'm choosing this phase to be 1. That is, whatever I get by taking this generator, that's what I'm calling my E alpha plus beta up to a real factor. That's just a phase choice. So one commutated down, E alpha, E beta. By the way, I have switched from E plus alpha to E alpha simply because alpha vector having length 1 means these two are the same. We have to be careful when it comes to other vectors, in particular for beta in this example, because beta has a different length. So E plus beta and E beta are not the same. E alpha and E plus alpha are the same. So this is a perfectly nice commutation relation to write down. Well, then we can take the commuter of E alpha with this, or we can just take this. That is, I hope everybody knows this notation, right? The repeated commutator notation.
No, sir.
It's just E alpha is commutated twice with E beta. This is a notation which we often use when we write things down like the Becker house of lemma, for example.
That's okay.
This is E alpha commutated with E alpha comma E beta. That's basically what it's going to be. It's going to be root 3 by 2 times E alpha. So that's the same thing as this. I could have dropped the root 3 by 2 factor and just found out this commutator as well. But what is this going to be? This is going to be root 3 by 2 times, what do you get now? Then you apply j plus twice on 3 by 2 minus half. That's what you're really doing, right? Sorry, j plus twice on 3 by 2 minus 3 by 2. So what will you get?
E2 alpha plus beta with an additional factor.
Of course, the question is what is the additional factor? Simple, it's just think of SU2. That's what you're doing. You get S root 3 by 2 the first time. What do you get the next time? Next time, this is J plus acting on this state, right? So what factor does it give you? Just forget all this. Just think of J plus square acting on this. What will this be? What would this have been? Elementary quantum mechanics. Of course, here you will get an extra 1 by 2 simply because there are two 1 by root 2s. But that's really not that important. As you saw, you get root 3 the first time around, then j plus, sorry, not 3 by 2 minus 3 by 2. 3 by 2 minus 3 by 2, on that you're acting j plus square. So apart from the root 3, what other factor will you get? 3 by 2 minus half. How much is that? Yeah?
So I don't remember the exact form of the factor.
3 by 2
And
minus
this is something which everybody must memorize. This is,
J plus n minus 1.
and it's pretty easy to remember. If you don't have to memorize, I never memorize. The point is you need to know that when you're raising, m equal to j will give you 0. This is for the raising. For lowering is j plus m to j minus m plus 1. Again, easy to remember where the plus sign or minus sign goes. Just remember which one is killed. The highest base state is killed for raising, so root over j minus m into j plus m plus 1. J minus m equal to j will kill it. So here, this what you have is 3 by 2 minus half, so plus half. That of course is 2. And 3 by 2 minus plus minus half plus 1. That's also 2. So what you get is root 3 into 2. Right? Is that okay?
Yes, sir.
So what should you get here? That's what you got with using j plus square. What should you get if using e alpha twice here? If you apply j plus twice, yeah.
Could you repeat the question?
If you apply j plus twice, this is the old, this factor, the factor I've used here, this definition is the old definition. That is without the root 2. Hold on,
It's
let me
going
just
to be
open the
just
door.
1.
Let me open the door. Oh. Okay, so as I was saying, these factors that I wrote down, root over j minus m, j plus m plus 1, they come with an extra 1 by root 2 in our example, in our application right now.
So just root 2.
So you get a 2 by root 2 in our example. But that should give you a root 3, right? After you cancel everything. Is that correct? I'm insisting on this is because this is where I can't seem to agree with what Georgi says. I don't know whether Georgi's book has come up with a new edition with a correction or something. This is the second edition I'm looking at, so I don't know. Because what Georgi says is that this is root 6. And I'm not so sure whether that's right. What Georgi says is that you get an extra factor of 2. I simply can't see why that should be, unless I made some stupid error in the calculation, which I can't spot. Okay, so you see, this is what actually took me most of the morning, because I tried to see several times ways whether I've made a mistake. I couldn't spot one.
Sir, is there a check, like we know what the actual commutation relations are. So does Georgia reach the same conclusion?
Well, G2, I will have to find out what G2's commutation relations are from somewhere. I don't
Sir,
yeah.
I mean, I think the initial factor for E alpha E beta should be root 3 by 4.
That would be a dangerous thing to have, because then the first of Georgi's results would be wrong. But anyway, let's see. whether that should be root 3 by 4. It's
I
3
mean,
by 2 plus 3 by 2, right? There's a top.
yeah.
Into 3 by 2 minus 3 by 2 plus 1. The lowest one is simply always 2j, root 2j, right? Because this one is always 1 when m is j. Sorry, m is minus j for the lowest one. So this is 2j and this is 1, always. So this is root 3 in the numerator and root 2 below from 1 by root 2 here. So it is root 3 by 2. It's not root 3 by 4.
Okay.
And by the way, that would have made it even worse. As I said, Georgia has an extra root 2 here. If you had put in a 1 by root 2, even more 1 by root 2s down here, that would have made my result diverge even further. So this is a, okay, it's true that we could have actually looked up G2's algebra in some other book. I just didn't bother to do that simply because, well, I'm pretty sure there are plenty of books which actually list that. G2 just doesn't happen to be that important in algebra for physics, that is, ordinary physics book would have that. Other books would. But the problem is once you get that factor messed up, all the subsequent terms will essentially have the same problem. So I'm not sure. I would ask you all to check carefully whether what I'm doing is, whether what I've done is right or whether what Georgi has here is right. And that's the trouble with trying to follow a textbook, because then if it doesn't agree with what you're doing, either the book has messed up, which is unlikely, or you have messed up, which is way more likely, but then it's really troubling, because then you, until and unless you can see why you have messed up or where you have messed up, it becomes a nagging point.
Sir, if the George's results were true, then the square root j minus m, that whole factor should be 2 root 2, right? I mean, 2 root 2 is kind of not possible with 3
No,
by
I
2.
know that factor cannot be 2 root 2. All I'm saying is, am I missing something completely in this whole argument?
If E alpha E beta commutation is correct, like root 3 by 2 E alpha plus beta is correct, then the only other explanation would be the square root should be 2 root 2 in the second
Oh,
commutation.
you're trying to back calculate, right?
Yes, sir.
No, it might also be that I'm missing out something in the definition somewhere, or maybe I'm reading Georgi wrong somehow. I don't know. Can't seem to be doing that. I don't seem to be doing that. What Georgi says is that the double commutator of E alpha with E beta is root 6 times E2 alpha plus beta. And I'm missing a factor of root 2 there. Anyway, you can of course press on with the assumption that, okay, Georgi must have made a mistake, which is a hell of a thing to say about a Nobel laureate, but still. People do make mistakes, so that's possible. By the way, the next thing that you would have to do is take the triple commutator. Yes, you can raise it 3 times, get a factor, which again does not match Georgia is the one which I'm getting, simply because of that root 2 mismatch that we had. Otherwise, it's just what do you get extra when you hit 3 by 2 half with the j plus. Straightforward. Now, one possibility which is there is that Georgia simply forgot. This is pretty arrogant of me to say, but Georgia may have simply forgot that he's dealing, the second time around, he might have forgot that he's dealing with this extra 1 by root 2 in the definition of j plus. Just use a standard factor of 2, which comes out in the ordinary SU2 case. Either way, I seem to disagree with what he has got. Anyway, once you finish this, you can easily calculate this commutator. That's trivial. Modulo the problem that I'm talking about. And the other one that you will need, this of course leads you to E3 alpha plus beta with a factor which you can easily figure out either following Georgi or following my calculation. and getting two different results either way. And the other positive truth that you have is 3 alpha 2 beta, which means you have to try E beta with whatever you have so far. That is, you have to try E beta on E alpha E beta 3. Well, the one thing you have to remember now is that E beta, when you apply it on E alpha E beta 3, this is actually E3 alpha plus beta, right? Now, this is a member of an SU2 subalgebra generated by E beta, E minus beta, and E beta, E3 beta. What is that SU2 subalgebra?
Half, spin half.
That's a spin half, right? Because it can only be raised once and no further, and this is the lowest state of that, right? Is that okay?
Yes, sir.
So what you should get is an extra factor, apart from the factor, whatever factor you have here in the E3 alpha plus beta definition, that is the vector at which Georgia and I disagree. What extra factor should you get because of E beta acting on this?
One by root 2.
No. You would have got 1 by root 2 if you had acted with E plus beta. That would have given you 1 by root 2. That's the SU2 factor for spin halves. But E plus beta is not E beta. Remember, E plus beta is E beta by the length of beta. And the
So
beta
3
is
by root 2.
no,
Root 3 by 2.
root 3 by root 2. The root 3 comes in simply because E plus beta has a length. This E beta which is sitting here is not E plus beta, right? That didn't bother us with E alpha because alpha vector had a length of 1. Beta vector having a length of root 3 means you have an extra root 3 factor. That's it. So that is sort of trivial. So basically what you can do is you can rewrite all these roots as repeated commutators of E alpha with E beta. That is, just to round off, E alpha plus beta we have already found out is root over 2 by 3. That's taking the root 3 by 2 to the other side. E alpha E beta. E2 alpha plus beta, that is where I have a problem. Georgia says is 1 by root 6. So what I said, of course, was not 1 by root 6. What I said was 1 by root 3. And E3 alpha plus beta, according to Georgia, is 1/3. I'm just reading from Georgia right now. Good thing that you can't see me read from a book right now, because I have this, habit of coming to the class after mugging up everything, so that people think that I know I can work out everything immediately without looking at my notes. But now I have the luxury of the fact that you cannot see me, so I can simply read off from the book. This is what Georgia says. I don't agree, but that's what you need to work out yourself. And E3 alpha plus 2 beta, according to Georgia, is root 6 by 9. E beta with the triple commutator of E alpha E beta 3. Now, the point is, everything else that you want to figure out, you can figure out every other commutator that you want to figure out. That is, how much is say E alpha plus beta, E2 alpha plus beta. Since E alpha plus beta and E2 alpha plus beta are given in terms of repeated commutators, you can just use a Jacobi identity to find out what the relationship is going to be. Okay? That's a lengthy calculation, but in principle, you can complete the whole algebra calculation pretty straightforward. Is that okay?
Yes, sir.
Of course, this will be something E3 alpha plus 2 beta times something. But what that factor will be, you can find out from this calculation. So my point is, if you know the simple roots, okay, modulo the factor which I'm finding difficult to wrap my head around right now, it's sort of established that if I give you the simple roots, or in fact, if I give you the Dinkin diagram, which essentially tells you what the simple roots are, you can find out the entire algebra, not only all the generators, which you already did before, but actually find out all the entire algebra. Of course, this and working out the G2 algebra will take some time because I have plenty of pairs which I have to work with. Some of them are pretty straightforward. For example, how much is this? Come on, these are straightforward.
0.
It's 0 because 5 alpha 2 plus 2 beta is not a root. We've already worked out all the positive roots, right? So some of them are pretty straightforward. E alpha plus beta, E2 alpha plus beta, on the other hand, is non-zero. Is E3 alpha plus 2 beta into a factor, which you should be able to figure out. That's our homework. Okay, whatever disagreements we may have about this factor and all this, either assuming that this is correct, the Georgia version is correct, or my version is correct, whichever it is, you should be able to find out what factor sits in front of E3 alpha plus beta plus 2 beta by using the Jacobi identity carefully. Okay? So, and then all the, of course, there are negative roots with which you can figure out the thing. E minus alpha's action is easy. You don't have to really use a Jacobi identity to find out the work which E minus alpha does on E alpha plus beta or E2 alpha plus beta or 3 alpha plus beta. You need, why? Because you know it's a spin 3 by 2 algebra, so you could just use that. But E minus alpha acting on E3 alpha plus 2 beta, you have to work out. Okay? Again, if the derivative property actually would make life rather easy here. These are doable. It's just that writing down everything takes a long time. So I'm not going to bother completing the calculation. Also, of course, then I cannot cheat from Georgia because Georgia has not done anything else. So I can't copy whatever he has written. Okay? So this is the second part of the program complete. That is, our program was find all the positive roots from all roots, find the algebra from the simple roots, and then find the representations, that is, the other irreducible representations as well from the simple roots. So that's going to take me at least one more day, if not a bit more. Okay. I will not, I don't have much time today, so I will not start the whole thing. I will just tell you one thing, which is you essentially find out the highest weight state for a representation and then use the lowering operators to lower and get the entire representation. How do you find the highest weight state? By definition, it's the state which will be killed by all the generators corresponding to positive roots. Okay, generators corresponding to positive roots is a bit of a mouthful, so I will just be messy and incorrect and say killed by the roots. So if a state is killed by all the positive roots, then you know it's a highest weight state, right? And then You don't even have to find out whether it's killed by all the positive roots. You just have to find out whether it's killed by all the roots, all the simple roots. Why? Because you know that the positive roots, okay, the positive, okay, how are the generators corresponding to positive roots connect, how do they connect with generators corresponding to simple roots?
So could you repeat the question?
The point I was trying to make is, okay, there this messy language I've been using, trying to shorten the words, will not really work very well. So let's say what we are saying is that a highest wave state is one which is killed by the generators corresponding to all the positive roots. But I'm claiming that you don't have to look at generators corresponding to the positive roots, all of them. All you have to do is look at the generators corresponding to the simple roots. A highest weight state is simply one which is killed by the generators corresponding to the simple roots. You don't have to look at all the positive roots, just simple roots will do. Which means for G2, for example, it will be a huge simplification. You don't, G2, you have 6 positive roots, right? But only 2 simple roots. So only 2 simple roots will tell you everything about the representation. That is, which one is, it will help you identify which one is the highest weight state, and then you can go down from there. But the question is, why is that true? Why is it correct to say that if a state is killed by all the positive roots, killed by all the simple roots, then it's also killed by all. So, okay, let me just stop the messy language and try to put it correctly. If a state is killed by the generators corresponding to all the simple roots, how am I so sure that it's going to be killed by all the generators corresponding to all the positive roots?
Because positive roots are like commutators of some simple roots. So like
Okay,
after
you're right.
expanding.
It's just you're right, except that the language would have been not the positive roots, but the generators corresponding to the positive roots are commutators of generators corresponding to simple roots. Right? Positive roots are, if you look at the roots, roots are just the vectors. So positive roots are sums of simple roots. But what we have just found out in the algebra part of our program is that the generators which corresponding to the positive roots, like E alpha plus beta, E2 alpha plus beta, etc., these are commutators or multiple commutators of the generators corresponding to simple roots. So, well, that's precisely why I said let's not use the messy language, because roots are not commutators, but generators corresponding to positive roots are commutators. So if you know that something is killed by all the simple roots, you can just use, say, you know something is killed by E alpha, E beta. So E alpha acting on some state is 0, E beta acting on some state is 0. That's my highest weight state for either SO3 or G2, let's say. Then E alpha plus beta, which is the other positive thing that I should look at least for G2, is simply, apart from the factor, is simply E alpha, E beta acting on 0. But that has two terms, E alpha, E beta, which kills 0, and E beta, E alpha, which also kills 0. So you get 0. Okay. So in order to check that something is the highest weight state, you don't have to worry about all the roots, all the positive roots. You have to just check whether it's killed by all the simple roots. So that cuts down the job a lot. And of course, this result. Remember, this result for minus v minus q works perfectly well for all representations, not just for the adjoint representation. The adjoint representation had the advantage that this w was also a root, so you could just use it in both ways. You could just argue that twice alpha dot beta by alpha mod square has to be an integer, and twice beta dot alpha by beta mod square would also have to be an integer. For other representations, of course, you will not say anything about what twice w dot alpha by w square is. That at least has no such significance, right? Because w cannot raise or lower, only alpha can. So we will use that and use this to complete the construction of the representations in the next class. So Thursday you said, right?
Yes, sir.
So
So if
Thursday.
it's a if nobody has a problem, just let me know.